Okay, here we are. We're going to talk about reactions of aromatics. Actually, this is a continuation of a discussion we've been having for several days. You may remember that we started out this discussion by reviewing quite a few different electrophilic aromatic substitution reactions. We moved on to Sandmeyer chemistry, and more recently we started talking about the formation of di, tri, and polysubstituted aromatics. In order to have that discussion, we needed to know something about which functional groups are activating and which are deactivating, and what are the directing effects of each of the functional groups. So we're going to review all these things, and we're also going to cover some new material. Let's start with electrophilic aromatic substitution reactions. Here's a nice, concise review of all the electrophilic aromatic substitution reactions we learned. They include chlorination, which is going to use molecular chlorine and iron trichloride. Bromination, using molecular bromine and iron tribromide, my goodness. Iron tribromide with bromination. Sulfonation, sulfuric acid and sulfur trioxide are the reagents. Nitration, nitric acid and sulfuric acid are the reagents. Friedel-Crafts alkylation. Here I start with an alkyl chloride and react it with aluminum trichloride in order to produce the new alkyl benzene. We have to be aware, however, that this reaction is limited. Carbocation rearrangements are a real possibility when we use straight chain alkyl chlorides in which the chain is 3 or larger carbons, 3 or more carbons. So for example, 1-chloropropane would not give rise to propylbenzene, but rather propylbenzene as a minor product, and the major product would be isopropylbenzene due to a carbocation rearrangement. Generally speaking, we want to avoid those carbocation rearrangements because it makes the product slates messy, so we only utilize Friedel-Crafts alkylation reactions where we're going to get a clean product out. And then there's the Friedel-Crafts acylations using an acid chloride and aluminum trichloride. Now in this case, there's no limitation on the R, so R can be a long straight chain, and in fact that's how we achieve the formation of something like a butyl benzene. I would use a 4-carbon acid chloride in the presence of aluminum trichloride to do the corresponding Friedel-Crafts acylation. Since it's a 4-carbon acid chloride, there's 1 carbon, and then 3 would be tied up in that R group. And then I can reduce the acylated product to the alkyl group using either a Clemmensen reduction or a Wolff-Kishner reduction, and I'm sure we'll see examples of those as we go today. And then finally, if you want to deuterate all 6 of the positions around the ring, you can do that very easily using D2SO4. So that's a quick review of our electrophilic aromatic substitution reactions. Let's look at the Sandmeyer chemistry. The Sandmeyer chemistry requires formation of this species in this box right here, this diazonium chloride, benzene diazonium chloride. But to get there, we've got to march through several steps. We've got to nitrate using standard nitration conditions, reduce the nitro group using H2 palladium to aniline. Here I have an NH2 group on board. That makes the molecule aniline. React aniline with nitrous acid HCl to produce the diazonium chloride. So when we talk about Sandmeyer reactions or Sandmeyer chemistry, we're really talking about reactions of this benzene diazonium chloride, and they're numerous. So for example, treating it with copper bromide will result in bromination. Copper chloride, chlorination. Copper cyanide, put a cyano group on board and that becomes benzonitrile. If we treat the benzene diazonium chloride with fluoboric acid, we can put a fluorine on. If we treat it with Ki, we can put an iodine on. If we treat it with sulfuric acid, we can make phenol. Hypophosphorus acid simply replaces The diazonium with a hydrogen takes us back to benzene, and that becomes a convenient way to make deuterobenzene. Using deuterohypophosphorus acid, we can add one deuterium onto the ring in this way. Much of our discussion as we proceeded has been on the formation of di and tri and polysubstituted aromatics, and this is the part we're going to start with today in some detail. We want to appreciate what it means to be an activating group or a deactivating group, and also we want to learn how we're going to use these directing effects in order to achieve various syntheses. So let's first review the table that I gave you some time ago, where we have both directing and activating, deactivating effects summarized. Up in this top box, I have the strongly activating groups. They include the amino group, whether it's just NH2 or a primary amino group attached to one carbon, or well, that would be secondary because the other carbon is benzene, which isn't shown here. So a secondary amino group attached to benzene plus another carbon, or a tertiary amino group attached to benzene and two other carbons. All of those are amino groups, amino functional groups, and they're all strongly activating. Likewise, in phenol, we have an OH group on board the benzene ring, and it's strongly activating. If I replace the hydrogen with an R, I have an ether, and the oxygen of the ether is directly attached to the benzene ring. All strongly activating groups. We talked about why those are so strongly activating. They have everything to do with the fact that the lone pair on either the nitrogen or the oxygen can be dumped into the pi system, creating extra electron density in the ring, making it more nucleophilic and more likely to react with electrophiles. They are strongly activating because of the lone pairs, and we're going to refer to that as a resonance effect. All of the activating groups are orthoparadirectors, including those that are strongly activating. Now we move down to the alkyl groups and the amide group. They're activating, not necessarily as strongly activating as these up here, but they are still nonetheless activating. And so what does it mean to be activating? It means that the reaction of an aromatic compound that has one of these activating groups on board would be faster than the corresponding reaction taking place with benzene alone, minus these activating groups. So activation and deactivation have everything to do with the rates of the reactions that we see. The reactions will be faster when these groups are on board. But these ones down here, the alkyl group and the amide group, they're not strongly activating, they're just activating, but activating nonetheless, and orthoparadirectors. Now if we move down to the bottom of the table, you see all these deactivating groups. They include any of the groups in which there's a carbonyl directly attached to the aromatic, including ketones, which are shown here, sulfonic acids, nitro group, the nitrile group of benzonitrile, and then this ammonium ion. This is a quaternary ammonium ion. The nitrogen is attached to benzene, that's one carbon, and three other carbons, and hence it has a formal positive charge. All of these are deactivating groups, and they're meta-directors. Now the reason that these are deactivating is that they all pull electron density out of the ring. Just the opposite of what we discussed up here. So with the amino and the hydroxyl group, those lone pairs allow us to push electron density into the ring. We call them electron donating groups, whereas all of these deactivating groups actually pull electron density out of the ring. They're electron withdrawing groups. Because they pull electron density out of the ring, they make it less nucleophilic and less reactive. And then there's the oddballs. The halogens are most definitely the oddballs. Fluorine, chlorine, bromine, iodine. They're actually weakly deactivating, for reasons we'll discuss in a minute, but nonetheless orthoparadirectors. So let's start there. Let's talk a little bit more about the halogens and try to understand why it is that these things are true. So there's an example of an aromatic ring, a benzene ring, substituted with a halogen. I'm not even going to specify which one it is. We'll just call it X. It can be any of the halogens. And what we notice is that the halogen is a very electronegative atom. I mean, fluorine is the most electronegative atom on the periodic table, and all of the halogens are fairly electronegative. And as we've discussed many times before, they're more electronegative than carbon. So for the carbon atom that's directly attached to the halogen, there's going to be a bond dipole moment, as shown, such that the halogen is actually delta negative and the carbon is delta positive. And so we can see by placing a delta positive at that carbon that essentially we're pulling electron density out of the ring. This is another electron withdrawing group. When we pull electron density out of the ring through this inductive effect, it's inductive because the electron density is being pulled through a sigma bond. So the inductive effect is such that we're reducing the electron density in the ring. It's being pulled out toward the electronegative halogen. That's going to slow down reactivity because remember, we're talking about electrophilic aromatic substitution reactions here, and this electrophile wants to react with a juicy nucleophile, one that's rich in electron density. Positively charged species are attracted to negatively charged species. This electrophile wants to see lots of nucleophilicity, lots of electron density. But when the halogen's on board, this inductive effect is going to reduce that. So that's the inductive effect. The truth of the matter is, this inductive effect also held when we had, for example, aminobenzene, aniline. Here, the nitrogen is once again more electronegative than carbon, so there was an inductive effect there, and that would seem to reduce the reactivity in the ring as well. Of course, the nitrogen is not as electronegative as halogens, so this effect would not be as large, but this seems to be at odds with what I've told you in this table. Here you see that the amino group is a strong activator. It's not deactivating, it's a strong activator. Well, this is also true for phenol, because oxygen is also more electronegative than carbon. So there's going to be a bond dipole moment, same direction as the bond dipole moment in the halogen substituted benzenes. All of these are inductive effects. All of these point to the fact that these groups are electron withdrawing. And all of those should make these deactivating. This electron withdrawing effect should make each of these deactivating. Well, clearly, that's not the case. The amino group and the hydroxyl group are strongly activating. They're not deactivating. We've talked about the fact that they actually pump electron density into the ring. What's going on here? Seem to be having two different stories. Well, that's because it's not a complete story yet. We do have this inductive effect, and this inductive effect is important, but there's also a resonance effect. And it's going to turn out that most of the time the resonance effect trumps inductive effects. So for example, while it was true that both the amino and the hydroxyl groups have an electron withdrawing nature if we consider inductive effects because of the fact that they're a bit more electronegative than carbon, it's also true that with those lone pairs they can pump electron density into the ring through a resonance effect. And we can draw these resonance forms as we did in class the other day, where we see this resonance effect in action. What this resonance effect tells us is that not only some of the lone pair electron density pumped into the ring, but when that happens through this resonance effect, it is the ortho position, ortho to the hydroxyl group, the para position, and the other ortho position, which share in the negative charge density. That in turn explains to us why it is that, number one, this is an activating group because this is a powerful resonance effect. Remember, resonance effects trump inductive effects. There's lots of extra electron density in the ring now. This is a powerful resonance effect, but also we understand why it is that the electrophiles would be attracted to the ortho and para positions, hence why it is that the OH group is an ortho-para director. So now, this makes some sense. When there's a lone pair on the heteroatom attached to the benzene ring, you get an activation through a resonance effect, and it's an ortho-para director. Well, back to our halogen. If you look carefully, we've already talked about the fact that there's this inductive effect because the halogen's more electronegative than carbon. We're actually sucking electron density out of the ring. Withdrawing electron density out of the ring means we're deactivating the ring. But looking carefully, the halogen also has lone pairs. Just like the amino group has a lone pair, just like the hydroxyl group has two lone pairs. So there should also be a resonance effect for the halogens. And indeed there is. So I can take any of those lone pairs and pump them into the pi system as well. And you see that I'm on my way towards drawing very analogous resonance forms. Here I have a lone pair and a negative charge at the ortho position. I can further delocalize to the para position. And finally, I can delocalize over to the other ortho position. These resonance forms look exactly like the resonance forms I had for phenol. So why is it that in the case of phenol we say the hydroxyl group is a powerful activating group, but in the case of the halogen substituted benzenes they're actually weakly deactivated? Well, it all comes down to these two effects. The inductive effect and the resonance effect. For the halogens, as well as for the amino group and the hydroxyl group, the inductive effects and the resonance effects are working against each other. In all three cases, the inductive effect is pulling electron density out of the ring. It's an electron withdrawing effect, leading to a deactivated ring. The resonance effect, on the other hand, is taking that lone pair electron density on the heteroatom, pumping it into the ring. It's an electron donating effect, leading to an activation. So they're working against each other. The inductive effects are deactivating the ring. The resonance effects are activating the ring. For every substituent except the halogens, the resonance effects trump inductive effects. It's true for every single substituent we'll encounter except the halogens. It turns out that the halogens, being so electronegative, are the only functional group in which the inductive effects trump resonance effects. And even in the case of the halogens, it's not a big trump. In other words, the inductive effects don't win out by very much. The halogens are weakly deactivating. Just barely deactivating, but deactivating nonetheless. However, when the electrophile comes around and looks at the halogen, it is most definitely interested in the ortho and para positions because of the resonance effect. With the resonance effect, we see that's where the electrophile would be most interested to add. So the halogens really are the oddballs. They can't decide whether they're activating or deactivating. In the end, the inductive effect wins out barely, only because they are amongst the most electronegative atoms on the periodic table, but nonetheless it is still an orthopara director. Now in the case of the deactivating groups, we don't have to worry about such things. In fact, if we go back and look carefully at nitrobenzene, which we examined earlier in class, you see a couple of things. Number one, the nitro group has this positively charged nitrogen on it. That makes the nitrogen even much more electronegative than it would normally be. And what we're going to see is that there is a powerful inductive effect here. The nitro group is going to pull electron density out of the ring inductively simply because there's a positively charged nitrogen. But at the same time, as we've already shown in class, there's also a resonance effect. I can take the pi electrons, kick them out to the nitrogen, and I'm on my way towards delocalizing a positive charge around this six-membered ring. So you can see that the resonance effect is also pulling electron density out. In the case of the nitro group, both the inductive effect and the resonance effect are deactivating the ring. So there's no question about it. The nitro group is a deactivator no matter which effect you look at. In fact, that's true with all of the groups here that are listed as deactivators. The carbonyl group, the sulfonic acid, the nitro, the nitrile, and the ammonium ion, they're all clearly deactivating. No hint of activation there. They're all meta-directors because the positive charge is going to be delocalized to the ortho and para positions, and the electrophile would prefer then to go meta. Okay, so that's an important discussion, and hopefully helps to explain why it is that the halogens are so odd. I think we're ready now to just start looking at some example reactions in which we try to prepare either a di or tri or other polysubstituted aromatic. So let's, for example, start with toluene, and let's try a Friedel-Crafts acylation. And ask the simple question, where will this new acyl group add to the toluene molecule? Well, if we go back to our table, we see that alkyl groups are activators and orthopara directors. And that's what we have on board. We have a benzene ring with an alkyl group, a methyl group on board. So that means that the molecule toluene is going to react faster than benzene would itself. If this were a reaction of benzene, the reaction with toluene will be faster, and it will take place primarily at either the ortho or para positions. That's ortho and para with respect to wherever the alkyl group is. So we would expect two products. Which would look like that. It's hard for us to predict yields, and I'm not asking you to do so. All I want you to know is that alkyl groups are orthopara directors, and so in this case you would expect two products. In all likelihood, the para product would be the major product, but again, I'm not asking you to identify that as the major product, just to know that both ortho and para would form. Okay, so that's an example. Let's look at another. Here's one. We have a methyl group and a halogen, a fluorine atom on board. They happen to be para with respect to each other. The question is, where will the next electrophilic aromatic substitution reaction go? In cases like this, where there are two groups on board, here's how we do it. The methyl group is an ortho-para director. Ortho and para relative to the methyl would be here and here. The para spot is already taken by the fluorine, so we can ignore that one. But there are two ortho positions that the methyl group could direct the next reaction to. The fluorine, as we've just discussed, being a halogen, is also an ortho-para director. The ortho spots are here and here, and the para position is already taken by the methyl. But it's going to turn out that we can ignore the fluorine here, because in cases where you have two or more substituents on board, for directing effects, all you have to consider is the most activating group. Well, the methyl group is an activator, because it's an alkyl group. The fluorine is a weak deactivator. So clearly, of the two groups, alkyl versus halogen, the alkyl group is the most activating, so that's the one we're going to pay close attention to. That's the one that's going to rule the day with regards to directing effects. Consequently, all we have to worry about are the ortho and para positions, but again, the para position is already taken. This nitration reaction is going to go to one of these ortho sites. It turns out that because of the symmetry in this structure, it doesn't matter which ortho site you choose, you get the same structure. So there's our product. This predict the product problem would have this answer and only this answer. Let's look at another one. Here I have a phenol, which is substituted with a methyl group in the para position. And let's see, what reaction do I want to run? I want to run a sulfonation. So I'm going to take H2SO4 and SO3 and ask the question, what would the product look like? Once again, we've got two or more substituents on board. This time they're both activating groups. But the rule is that whichever group is the most powerfully activating, that's the one that rules the day. It was easier in the last example because one of them was activating and one of them was deactivating. So it was a no-brainer. The activating group is the most activating group. It rules the day, and our product was as shown. Here I have an OH group and a methyl group. They're both activating, but if I go back to my table, I will remember that the OH group is strongly activating, whereas the alkyl group is just activating. Consequently, the most activating group is the OH group. It's an ortho-para director. There are the ortho spots, the para spots already taken. So the reaction has to go at one of the two ortho positions. And there would be my product. Now this leads to an interesting related discussion. It turns out that these amino groups in the hydroxyl group, part of aniline and phenol, and or closely related structures like this ether or these substituted anilines, they are so strongly activating that sometimes it's hard to stop reaction from proceeding further. For example, if I started with this aminobenzene and I tried to, let's say, chlorinate, I'd have to be really certain that I controlled the stoichiometry of this reagent. This amino group is an ortho and a para director, so assuming I strictly adhered to one equivalent of chlorine, I would expect a mixture of the ortho and para product. But if I didn't strictly adhere, if I used an excess, let's say I used 2 equivalents of chlorine, it would be hard for me to stop there. This is such a powerfully activating group that the reaction would just keep going. And the most likely product would be the case where I have 1 ortho and 1 para chlorine formed. It is possible that you'd form a disubstituted with both ortho positions substituted, but in practice it turns out that those products are usually formed in very low yield compared to the case where you have 1 ortho and 1 para. So these powerfully activating groups, they can continue to react, and that can be a problem. Sometimes, however, it can work to your advantage. For example, what I'm about to show you is not generally true. This is a specific example. But if you take phenol, which again has that powerfully activating group on board, and you treat it with sulfur trioxide and H2SO4, these are sulfonation conditions. These are reagents now where we almost have to have a large excess. You don't run this reaction in another solvent, you run it in sulfuric acid. So there's a huge, enormous excess of sulfuric acid, and generally speaking, there'd also be an excess of the sulfur trioxide in this oleum solution. So we get a big excess of reagent and a powerful activating group. It turns out that this phenol compound will form a disulfonic acid in which you have 1 ortho and 1 para sulfonic acid. And this particular product is noteworthy, this particular reaction is noteworthy because you form this in basically 100% yield. It's a quantitative conversion. That's going to turn out to be very useful for us, as we'll discuss in a few minutes. Again, this is not a general case. Not all orthopara directors will do this. In fact, this is specific to phenol. So if you take something like a methyl group and try to do the same thing, you won't get 100% yield of this product. This reaction is a unique one, but it's one that we'll take advantage of in a few minutes. Well, we figured out some of the basics of preparing di and tri and polysubstituted aromatics. Now we want to get into a little bit more detail. And by detail, I mean we want to get a little bit more sophisticated. And in order to get a little bit more sophisticated, we need to learn a few tricks of the trade. Trick of the trade number 1. One of those groups that I just told you is a powerful activating group is the amino group. And so if we wanted to run some sort of a reaction, I think a moment ago I showed you a chlorination, or if we wanted to run a bromination or an alkylation, it might be difficult to stop after 1 addition, particularly if we added an excess of reagent. But what we can do is we can acylate at nitrogen using a simple acid chloride like acetyl chloride. Now this is not a Friedel-Crafts acylation. Notice there's no aluminum trichloride here. This is just an acid chloride for acylation at nitrogen. The nitrogen atom is actually much more nucleophilic than the aromatic ring, so no catalyst is required. What I'm going to do is a nitrogen acylation, which means that I've added the acetyl group, this group right here, to the nitrogen. Now when we get into the study of carbonyl compounds, including acid chlorides, we're going to see this reaction again. So in some ways this is a prelude of some things to come down the road. But we need to know this reaction right now because it impacts our chemistry of aromatics. I started out with a powerfully activating amino group, and after this nitrogen acylation using an acid chloride, I have an amide. If we go back to our table, we see that the amide group is activating. It's not that powerfully activating group that the amino was, but it's activating. So consequently, if I'm worried that I'm going to overreact because I've got a powerfully activating group, maybe I'm worried I'm going to add more than one sulfonic acid or more than one chlorine in an electrophilic aromatic substitution, one possible path that I could take to avoid that would be to first nitrogen acylate to the corresponding amide. It's still an activating group. Run the reaction of interest, and then I can take that amide and convert it back to an aniline through a hydrolysis reaction. Hydrolysis can be achieved with H3O plus H2O or OH minus H2O. The hydrolysis will be clean and quantitative and take me right back to the aniline compound. So this we consider to be trick of the trade number 1. Let me show you an example of where this could be utilized. Here's a synthesis problem. I want to take benzene and I want to convert it into para-bromoaniline. Well, you might try to do this in a couple of different ways. You might, for example, try to brominate first and then figure out how you're going to add your amino group. The problem is the bromine atom is an ortho and a para director, so while you might be able to get some of this para product, you're also going to have some of the ortho formed. I'm going to make this problem a lot harder by saying free of other isomers. So in other words, I want to make this particular para-substituted product without any of the ortho isomer formed. Now, we're not always able to do this perfectly, but when you see a problem like this where it says free of other isomers, it means as free as possible. In other words, come up with the best possible synthesis. This is not the best possible synthesis, putting the bromine on first and then trying to put the amino group on second, because the bromine is not a very big atom. There's nothing going to stop addition at the ortho sites. However, if I put the amino group on first, I might be able to stop addition at the ortho sites altogether by first converting it into an amide. Let's look at this. First of all, how do we get the amino group on board? Well, that starts with nitration. Followed by reduction. So when you want an amino group, that's how you do it. Nitration followed by reduction. For reduction of the nitro group, we use H2 palladium. Now, we talked about this being a powerfully activating group. If I try to brominate right now, I'm going to no doubt put some bromine at the para position, no doubt put some at the ortho position, and because it's such a powerfully activating group, I might do both. Unless I rigorously control the amount of bromine I add, I could easily over-brominate. So what I'm going to do is I'm going to use that acetyl chloride. Remember, acetyl chloride looked like this. CH3, carbon double bond to oxygen, and a chlorine. And we can abbreviate it as acetyl chloride, ACCl. The acetyl group is that part right there, acetyl chloride. So all I'm going to do is I'm going to add acetyl chloride, and it is okay to abbreviate it like this. And when you N-acylate it, you have the acetylated nitrogen now. It's an amide, and it is okay to use that abbreviation. Now this new functional group, this new amide with the acetyl group on board, is actually sufficiently large. Here it is drawn out. There's the acetyl group. It's sufficiently large, and this carbon-nitrogen single bond is free to rotate, that this large group rotates around and around and effectively blocks these ortho positions from further reaction. Now that's not rigorously true. There would still be some reaction at the ortho sites, but it certainly slows it down. when this bond rotates around, which it's prone to do many, many times per second, this large acetyl group zips around and blocks these ortho positions, but not the para position. So if I were to brominate at this stage right here, I would get predominantly the para product. Would this be 100% free of the orthoisomer? Probably not. Almost certainly not. But it's going to be almost free of the orthoisomer. The orthoisomer would only be formed as a minor product. The parasite is so much more accessible in the presence of this large amide. So what was the advantage of converting the aniline into this acylated amide? Twofold. Number one, it helps to block the orthosites so that reaction predominantly goes to the para position. But number two, it also slows the reaction, the bromination reaction, down, because while this is an activating group, it's not powerfully activating, and I don't have to worry about over-brominating. Well, all that's left is to get rid of the amide through hydrolysis to go back to the amino group. So you can choose either basic hydrolysis, OH minus H2O, or acidic hydrolysis, H3O plus H2O. Don't use both, just pick one. When you hydrolyze the amide back to the amino group, you will not impact the bromine at the para position, and now we're done. That is the synthesis. So the overall synthesis was 1, 2, 3, 4, 5 steps, and it allowed me to produce the desired compound cleanly, free of other isomers, or at least as free as possible of other isomers. So that's trick of the trade number 1. And we can use that a lot. That's a very valuable trick. Let's talk about trick of the trade number 2. Actually, you already know trick of the trade number 2, but I didn't present it as a trick of the trade last time. Here's trick of the trade number 2. When you have an amino group, you can oxidize it using a peracid to a nitro group. And the nitro group can in turn be reduced to the amino group. In other words, the nitro and the amino group are interchangeable through these reactions. That is very, very useful. For example, what if I wanted to make this? Well, there'd actually be a couple ways to do this, but once I recognize that the nitro group and the amino group are interchangeable, it opens up new synthetic possibilities for me. If I didn't know that, I might look at this structure and say, okay, well, I have an alkyl group, which is an ortho and a para director, and so one way that I could run this synthesis would be to put the alkyl group on board first, and then once that's on board, go ahead and put the nitro group. Actually, that would be a pretty effective synthesis because, once again, I've got a fairly large group here. This is a large alkyl group. This carbon-carbon bond is free to rotate, and when it rotates, this ponytail here is going to zip around, blocking the orthosites. When I nitrate this, it's predominantly going to go para. So that would be an appropriate synthesis, an appropriate synthetic approach. But what about if I put the nitro group on first? Well, the nitro group is a meta-director, being a deactivator. It's a meta-director, like all the strong deactivators. So if I put the nitro group on first and then try to put the alkyl group on, I'm going to get the wrong product. That's not going to work. However, recognizing that the nitro group and the amino group are interchangeable, that gives me another approach to put the alkyl group in the para position. So let's look at two unique syntheses, both of which work to form the desired compound. We're going to start off with an approach where we add the alkyl group first. So here we go. You know that since this is a straight chain alkyl group, we cannot go ahead and try to run a Friedel-Crafts alkylation straight away. That will not work. There will be rearrangements, carbocation rearrangements. You'll form at least 2, if not 3, different alkyl benzenes. I should note that I want to make this free of other isomers. So once again, it's not okay to have all these different byproducts, including lots of ortho structure or lots of carbocation rearranged alkyl groups. Anything like that is going to turn it into a much less effective synthesis. I want to make this particular compound as free of other isomers as possible. So what does it mean? 1, 2, 3, 4 carbons is what I'm trying to add. 1, 2, 3, 4 carbon acid chloride. I'm going to run a Friedel-Crafts acylation first. This is our customary strategy. There's no problem with carbocation rearrangements when I run a Friedel-Crafts acylation, followed by a reduction. Now for this reduction, you have 2 choices. Either a Clemmensen reduction or a Wolff-Kishner reduction. This is the Clemmensen, this is the Wolff-Kishner. You don't need both, you just need one. And there you have reduced to the corresponding butyl benzene. Now at this point, because this group has 3 or more, actually 4 atoms in it, and there's a carbon-carbon, or at least a single bond, doesn't have to be a carbon-carbon bond, but in this case it is, a carbon-carbon single bond, this group is free to rotate. We would expect that the ortho positions will be blocked relative to the para position, and so when we run the next reaction, which will be nitration, we will get predominantly the para product formed. So there it is, we've done it. The synthesis is 1, 2, 3 steps. But let's try that other approach. Let's try to do the same exact synthesis, this time taking advantage of the fact that the amino and the nitro group are interchangeable. So here we go. I'm going to nitrate. And then I'm going to reduce. And now what I want to make is a compound in which this alkyl group is in the para position. Right now, if I tried a Friedel-Crafts acylation followed by a reduction, just like last time, I would acylate clearly in both the ortho and the para positions because the amino group is not very big. It's not going to block the ortho positions. So what I need to do instead is to treat it with acetyl chloride, which gives me the acetylated nitrogen, the amide, which is now large enough to block the ortho positions. Now I run a 1, 2, 3, 4 carbon Friedel-Crafts acylation. Now I've got 2 things left to do. One is I've got to hydrolyze the amide back to an amine, and the other is I have to reduce the ketone to an alkyl group. Really doesn't matter in this case which order you go in. I'm going to go ahead and hydrolyze first. That puts the amine back in place at the para position. And finally, I'm going to reduce the ketone. Now remember, for this reduction, unlike the nitro to the aniline reduction where we use H2 palladium, for the reduction of a ketone to an alkyl group, We have to use either the Clemenson or I'm going to choose the Wolff-Kishner reduction in this particular case for no particular reason other than I can. And there it is. This synthesis gets me to the exact same place. Oh, I'm not there yet, am I? I forgot. I'm actually trying to make this compound with a nitro group para to the butyl group. So one more step. MCPBA will oxidize the amino group to a nitro group but not impact the alkyl group. So how many steps? This is quite a few steps. 1, 2, 3, 4, 5, 6, 7 steps. Of the two syntheses, you'd have to say that this first one is better simply because it has fewer steps. 1, 2, 3 steps instead of 7. But both are acceptable. They're both full of good reactions that should all proceed in high yield. If you had this problem on a quiz or an exam and you gave me either the 3-step or the 7-step syntheses, I'd accept either one. Okay, so we've talked about trick of the trade number 1, which is nitrogen acylation. Trick of the trade number 2, which is interconversion of the amino and the nitro group. And finally, trick of the trade number 3. Trick of the trade number 3 is not really a trick at all. None of these are really tricks. They're just knowledge. Trick of the trade number 3 is understanding that one of the electrophilic aromatic substitution reactions we've studied, sulfonation, is actually reversible. That is, you can take and form the sulfonic acid through the reagents we've discussed, sulfuric acid and sulfur trioxide, and when you take a benzene sulfonic acid and you heat it up in the presence of H2O, and you do need the triangle because we're talking about boiling H2O here. This is not a reaction that will work at or near room temperature. It needs to be boiling water, very hot water. So we're going to take water, we're going to heat it up, and we can go right back to the benzene. That is, we can knock off